Hi everyone. Now that we've seen in section 11.4 the basics of polar coordinates, we're going to take a look at, in this next section, 11.5, some graphs of polar equations. Now this is the second section in your book that deals with polar coordinates. We'll deal with one more after this, so 11.4, 11.5, and 11.7 all deal with polar coordinates in one way or another. We'll take a look at some graphs of some polar equations in this section. And on the board behind me you can see some basic common polar graphs that most pre-calculus courses go over in one way or another. In this first video we'll talk about circles and lines, but in future videos we'll talk about rose curves, cardioids, which are shaped like hearts. You might see the word cardio in there, right? Cardioids belong to a more general family called limacons. So I didn't slip there, and that's a little French accent mark under the C. And this little accent mark means it's a soft C, so limacon and not limacon. And then this last one here, the lemniscate. Lemniscates look like figure eights. So we'll take a look at least one example of each of those in the videos that follow. So let's take a look at some examples and get started. We'll start with example 1 from the guided notes. So example 1, we want to graph the polar equation r equals 4. And remember from section 11.4 what r represents. R represents the distance from the pole, distance from the pole to my point. So if I start at the pole, we're looking for all the points that have a distance of 4 from the pole. And we remember the concentric circles that go out from the pole. So r equals 1, r equals 2. Each circle represents 1 unit, so r equals 1, 2, 3, and 4. So for instance, this point here is 4 units away from the pole, and it's in a direction of 0 radians. So remember, the direction is the angle in standard position. So if I remember what my quadrantal angles are, that gives me an indication of direction. So this point, this first point here, is 4, 0. Remember, this is in polar coordinates. And all the points where r equals 4 are going to be the points that lie on this fourth circle from the pole. So r equals 4 is going to be, in polar equations, polar coordinates, it's going to be, the graph of this is going to be the circle of radius 4 centered at the origin. So if I think about the other points that are on this graph, we've got the point 4, pi over 2. Okay. We had to be a little bit careful to identify this was polar here, or at least I did, just explaining it to everybody, because it's easy to think 4, 0, well, you could think of that as xy coordinates or r theta coordinates in this case, but here it's a little bit more clear. I'm talking about polar coordinates. I just wanted to be real clear with you there what I was talking about. And likewise here, for instance, if I pick something that's not a quadrantal angle, this is halfway between pi and 3 pi over 2, so that should give me an angle of 5 pi over 4. So we've got the point 4, 5 pi over 4 here. Everything we do in this section when we're graphing on polar graph paper, we're going to be in polar coordinates. All right, this is our circle, radius 4 centered at the origin, like I said. And it's not the only way we can think about a circle centered at the origin. Any of these points that I've written down, I can write. Remember, there are infinitely many ways to represent a point in polar coordinates. So if you think about the polar equation, for instance, r equals -4, you're going to get the exact same circle, radius 4, centered at the origin. I'll sketch that circle in real quick. So I've gone 4 units out from the pole. And just to show you why that is, the point here, well, we thought of this as the point 4, 0 in the circle on the left, but we can also think of this as the point -4, pi. So remember, we're traveling in the pi direction. If I go -4 units to the left, that's really the same thing as going 4 units to the right. So any of these points where r equals 4, I can think of as a point where r equals -4 just by reversing the direction. So here we've got -4, 3 pi over 2, and instead of 5 pi over 4 being the angle here, I can think of this as -4. I've just gone a little bit off screen there, excuse me, -4, pi over 4. So r equals 4, and if you look at your guided notes, the next example there, r equals -3 radical 2, you can approach the same way. You just need to get a decimal approximation on your calculator to determine where the circle should go. Now if I look at problem 3, we've got theta equals 5 pi over 4. So instead of saying what r equals, we're talking about what theta equals. I don't even really need polar graph paper for this one, although feel free to use some if you prefer. So theta equals 5 pi over 4. It's just telling me what direction I'm traveling in. So 5 pi over 4 direction, that's going to be halfway between pi and 3 pi over 2. So any point that's going in this direction, so let's say this is 1, 5 pi over 4. Any point in the 5 pi over 4 direction is going to satisfy this equation. So if you want to get even more basic, what does it mean to be on the graph of this equation? Well, the point has to satisfy this equation. So my point r, theta has to make this equation work. So any r value, doesn't matter what r is not in the equation, so we say r is a free variable, or r can be whatever it wants to be. I can say r equals 2. And I end up getting this entire half line. Now remember what I said before. I can think of these points as also in the 5 pi over 4 direction if I consider my r to be negative. So if I look at a point here, let's say this is, even though this is really, let's say 1 unit in the pi over 4 direction, I can think of it as -1 unit in the 5 pi over 4 direction. Right? So any point that's on this line is going to have at least one polar representation where the direction or the angle is 5 pi over 4. Now you can graph the equation in problem 4 similarly. Theta equals -3 pi over 2. You just find the -3 pi over 2 direction. So -3 pi over 2, you'd go clockwise 3 pi over 2 radians. And any point on this vertical line through the origin is going to have at least one representation where the angle is -3 pi over 2. So for instance, this point here, yeah, we could say it's 1 in the 3 pi over 2 direction, but we could also say that it's -1 in the -3 pi over 2 direction. So to summarize example 1, we've looked at two of the most simple types of polar graphs. R equals some number, whether it's positive or negative. So if I look at r equals a, this is going to be a circle centered at the origin, or I guess we're in polar coordinates, I should say pole here. Circle centered at the pole of radius absolute value of a. Okay, so I'm saying absolute value of a, that's going to cover my bases. For instance, if I'm looking at this example here, r equals -4 is going to be a circle of radius +4 centered at the pole. And if I look at theta equals some number, this is going to be a line through the origin. So it's a line through the origin or a line through the pole in the b direction. So like we saw here, this was a line through the pole in the 5π/4 direction. So remember, that's going to include even the π/4 direction, because I can think of any point with a π/4 direction as also in the 5π/4 direction by negating the radius. So, as I said, these are the simplest examples of polar equations we'll look at here. The next example here in the book, and I'm not going to go through this whole example, but the next example we're looking at is the equation r equals 6 times cosine of theta. And the first thing that the notes here suggest is, it says we could start by plugging in values of theta from the unit circle and creating a table. So selecting values of theta here, so it looks like we've got a decent selection of theta values from 0 to 2 pi, all our multiples of π/4. And if I plug in theta equals 0 to r equals 6 cosine of theta, we know cosine of 0 is 1, so 6 times 1 is 6. That gives me my r value. And then this gives me my point. So plugging and chugging, just like we did with unfamiliar functions back in college algebra. The problem with this approach in polar coordinates is that as you study this table, as you go down the line, you'll notice we only have 4 distinct points. So if I try to plot these points, you'll see what I mean. So we can start with 6, 0. So remember, these are polar coordinates, so I'm going 6 units out in the 0 direction. So if I label my quadrantal angles here real quick, say 6 units out in the 0 direction. Now if I'm looking in the π/4 direction, I'm going 3 radical 2 units out. I'm going to be somewhere around here, and I'm not being terribly precise with this, but take my word for it, the point's going to be somewhere around there. So radical 2 is about 1.4, so 3 radical 2, if you do the math, there's going to be about 4.2. 0 π/2 is my next point, so I'm going in the π/2 direction, but I'm actually not going anywhere. My distance from the pole is 0, so I'm actually at the pole here. So there's 0 π/2. And I guess I kind of lied a bit ago. I said I wasn't going to go through this whole thing, but I guess I am going to plot these points. So next point here, -3 radical 2, 3 π/4. So the 3 π/4 direction is going to be up and to the left in the second quadrant. I'm actually going to be going in the opposite direction because of that negative sign. So I'm going to have a point here. It's going to be sort of symmetric with our other point, 3 radical 2 π/4. This is going to be -3 radical 2, 3 π/4. And as an exercise, I encourage you to look through the other 5 points. For instance, -6, pi. you should see is the same as the 0.60. So going 6 units in the 0 direction is the same as going -6 units in the pi direction. And likewise with the other 4 points, you should see that we get the same 4 points again. So based on what we see here, it's difficult to know exactly what r equals 6 cosine theta really is. If this was a function from college algebra, we'd probably say we want to see more points before we can determine what the shape is. We might guess what the shape is, but it's kind of hard to tell. So if I were just guessing what the shape was, and you might have a different guess, but I would guess that maybe kind of like what we did in the last example, maybe I'd get a circle like this. That's a valid guess. It turns out to be that that's exactly what we do get, but there's nothing that says that, you know, we couldn't get a diamond shape like this. Right, there's a lot of wiggle room when we only have 4 dots. So let's think about this. Let's think about why we have some level of curvature here, why this isn't going to be a diamond. And that's where the method on the next page comes in. And this is the method we'll use with most of the polar equations that we encounter, except for the most simple ones like the circle and the line that we did in example 1. So method 2 here, it says graph one cycle of r equals 6 cosine theta on the theta r plane and use it to help graph the equation on the xy plane. So what this is asking us to do is pretend for a moment, pretend that we're looking at y equals 6 cosine of x and graph this in rectangular coordinates. So pretend we're looking at the corresponding equation y equals 6 cosine of x and graph it in rectangular coordinates. So I'm glad I was able to spell coordinates correctly while I was saying the first line. That's always hard to say one line and write something else at the same time. So glad we were able to spell rectangular coordinates correctly there. All right, so let's go ahead and do that. If I'm looking at y equals 6 cosine of x, that's actually a graph that should be really pretty familiar to us. So it's just going to be the standard cosine graph, and I'm just going to look at the interval 0 to pi here just to start. So if I think about what the cosine graph looks like, here's my basic shape. And if I'm looking at 6 cosine x, I'm going to have the point 0.06 here. So I'm looking at rectangular coordinates now. So this is x and y. So I've got 0.06. This is pi over 2, 0. So it might be a little bit disorienting at first to think about this, but these are rectangular coordinates. We're not looking at these in polar at this point. So 3 pi over 2, 0. And 2 pi comma 6. Okay. Now, the reason why it says graph on the theta r plane is because really, if I think about this as, I'll use another color here, r equals 6 cosine of theta. Theta is playing the role of x, r is playing the role of y. So instead of x, I can think of the horizontal axis as my theta axis, the vertical axis as my r axis. So we've got the theta r plane, like we normally refer to the plane as the XY plane. This is the theta R plane. And this is my graph. And if I think of this as the theta R plane, you'll notice that these points in rectangular coordinates have coordinates theta, comma R. Okay. Now what I'm going to do is I'm going to convert, so here's rectangular. There's the rectangular graph. Y equals 6 cosine of x. And I'm going to move now to the polar graph. So move this down. I'm going to move to the polar graph. R equals 6 cosine of theta. And what I'm going to do is I'm going to look at basically the four quadrants. So what's going on from 0 to pi over 2, what's going on from pi over 2 to pi, and what's going on from pi to 3 pi over 2, and then what's going on from 3 pi over 2 to 2 pi. Okay? So if I look from theta equals 0 to theta equals pi over 2, what's happening to my radius? Well, my radius is decreasing from 6 down to 0. Okay, and it's decreasing in a gradual way, in a continuous way. So I'm starting at the point 6 comma 0. And as time goes on, as my theta goes from 0 to pi over 2, so from 0 to pi over 2, my r is going to go from 6 down to 0. So I'm going to land at the point 0 comma pi over 2. Okay. So I'm thinking now we're in polar coordinates. So 6 comma 0, here's my r comma theta. R comma theta. So notice this is inverted from this. So these points were theta comma r. This is in polar coordinates r comma theta. And what's happening is that my distance to the pole is shrinking gradually. So I'm curving around like so from the point 6, 0 to the point 0 pi over 2 in polar coordinates. Now if I go from theta equals pi over 2 to theta equals pi, I start at the pole, right? When I'm going in the pi over 2 direction, my r is 0. And what's going to happen when theta equals pi is I'm going to be going in the negative direction. So as theta goes from pi over 2 to pi, my distance from the pole is going to go from 0 to negative 6. So as I'm looking at my second quadrant angles, my distances from the poles are all negative. So as I'm looking at my second quadrant angles, I'm actually going to be traveling in the opposite direction. I'm going to be traveling in the fourth quadrant. My distance is going to go from 0 to negative 6. You can see I'm actually going to end up at the same point I started. I'm ending up at the point negative 6 comma pi. As I'm going into the third quadrant, starting at the point negative 6 comma pi, still traveling in the negative direction. So in the third quadrant, if I'm traveling in the negative direction, that means I'm really going to be in the first quadrant. My distance from the pole is going to decrease from 6 to 0. So as I'm traveling through my third quadrant angles, remember my r is negative, so for my third quadrant angles, I'm going to be in quadrant 1. My distance is going to decrease to 0 until I get to the point 0, 3 pi over 2. And then in the fourth quadrant, my distance becomes positive again, grows from r equals 0 to r equals 6. So I trace the bottom part of my circle again. Now, in hindsight, in order to get the entire graph, we really didn't have to go from 0 all the way to 2 pi. All we had to do was go from 0 to pi, and then we saw that the graph just kind of retraced itself. So in general, with polar coordinates, 0 to 2 pi is a good starting point, but there's no rule that says that we have to use all of the points from 0 to 2 pi. Now, on the other hand, there's no rule that says 0 to 2 pi is going to be enough to generate my graph. So you might find with some examples that if you go from 0 to 2 pi, you don't get a graph that looks complete. So if that happens, you might have to expand your view to maybe 0 to 3 pi or 0 to 4 pi, and so on. So just a few more comments on this example. Let's get a fresh sheet here real quick. So remember what this looked like. This was the circle. It looked like so. So we had the point 6, 0, and you can think of this as 6, 0 in polar or rectangular at this point. What we have here is a circle of radius 3. Now remember the equation was r equals 6 cosine theta, but it's a circle of radius 3 centered at this point, which you can think of in polar coordinates as 3, 0, a distance of 3 from the pole in the 0 radian direction. Or you can think of it as the point 3, 0 in xy coordinates as well. So the radius of this circle, notice, is 3, and the relationship between 3 and the equation, notice the number in front of cosine theta is 6. My radius is going to be half of that. So in general, if I'm looking at the equation r equals a cosine of theta, the radius of that circle is going to be 1/2 the absolute value of a. So I kind of beg the question there, well, why am I saying absolute value? Well, I could potentially have an equation where I'm looking at r equals -6 cosine of theta. So how would that change the circle? Well, so for r equals -6 cosine of theta, if I go through the same exercise as we did before, let's try to graph y equals -6 cosine x, just the Cartesian equation, on the interval from 0 to 2 pi. What we would get is the mirror image of the graph that we got in our previous example. So I'm just sketching this out, not trying to be too terribly precise here. And we're crossing the x-axis still at pi over 2 and 3 pi over 2. So if I go through the similar type of exercise that we did before and I divide this into quadrants, so what am I doing in quadrant 1, quadrant 2, quadrant 3, and quadrant 4? Let's change our attention back to the polar form. So r equals -6 cosine of theta. So remember, my theta values are on the horizontal axis, my r values are on the vertical axis. So if I look in quadrant 1, I'm starting 6 units from 0 in the negative direction. So this is the point 0, -6, right? And I'm going -6 units. Remember, these are theta r coordinates. I want to go 6 units in the opposite of the 0 direction. So I'm going to be traveling actually in the pi direction. So I'm starting at this point here. So this is r comma theta, -6 comma 0. And as I go through the first quadrant, my r is always negative, and when I get to pi over 2, I'm back at the pole. Anytime I cross the x-axis here, that tells me I'm going to be in the pole in my polar picture. All right, because an r value of 0 means I'm at the pole. So here's my point 0 pi over 2 in polar coordinates. And you can see how this circle traces itself out. And likewise, we go through the same exercise in the second quadrant. My distances are all positive, so I'll leave that to you and this point as an exercise, so we get back to the point 6 comma pi. And you can see that again, we end up tracing our circle just on the interval from 0 to pi. You should check for yourself that if we go from pi to 2 pi, we end up tracing the same circle again. Now, this is what we get if we look at r equals negative 6 times cosine of theta, but if I look at r equals a sine of theta, we also get circles as well. I encourage you to do a couple examples as an exercise, but I think this would probably be a good time to introduce the graphing calculator. And we'll take a look at how to graph polar equations using the graphing calculator. So let's say I want to graph r equals 6 sine of theta. And let's pick another number even. Let's say r equals 4 sine of theta. Now, in order to access polar coordinates on the graphing calculator, I need to switch modes. So if you have a TI-83 or a TI-84, you should be able to hit the mode key. And just like we switch from radians to degrees and back, if I go one line below that, I'm looking for this POL option, and that's going to tell me that I want to graph in polar coordinates. So if I hit my y equals key, instead of y equals stuff, we're going to have r equals stuff. So if I want to type in, let's say 3 sine of theta, just to pick a different number than what we had before, notice this xt theta n button now gives me a theta instead of an x. So I've got r equals 3 sine theta, and chances are I'm probably going to have to play with the window a bit. Yeah, you can see I get a graph, but we're going to have to play with the window in order to get the picture we want. So I'm going to hit my window button. Now my theta, you can see I'm going from 0 to 2 pi. And this theta step tells the calculator to graph 1 point for every 0.05 radians. All right. Usually that'll be enough to give you a good picture, but if your picture looks a little sketchy, make that number smaller. It'll make your graph more precise, but more precision means the calculator takes more time to do it, so you don't want to make this number too small. The rest of this is just X and Y axis, my viewing window. So I'm going to go from negative, let's say 3 to 3 on the X, tick marks 1 unit apart, negative 3 to 3 on the Y, tick marks 1 unit apart, and let me hit graph. And you can see that this gives me something that resembles a circle. Now it doesn't look perfectly circular, but you can see that instead of a circle that opens to the right or to the left like we had with the cosine, now that we're looking at a sine function, now my circle opens up. And if I want to make this look a little bit more circular, what I can do is I can square my viewing window. So you can always square your viewing window by hitting zoom 5. And that's going to make your viewing window look square. So that's going to account for the fact that my calculator screen is not perfectly square, it's rectangular. So it's going to expand the x-axis accordingly, And now I have something that looks like a circle of radius 3/2, centered at the rectangular point 0, 3/2. All right. So you should go back and try to use the method that we went over here to verify what the r sine theta, the a sine theta graph looks like. So if I'm looking at a cosine graph, so r equals a cosine theta, your circle will either open to the left or to the right. It opens to the left if your a is negative. It opens to the right if your a is positive. And if I look at r equals a sine of theta, this circle is going to open either up or down. It opens up, like we saw in the graphing calculator, if a is positive, and it will open negative, or it'll open down if a is negative. So we'll see that as kind of a recurring theme with some of these other graphs, the cardioids and the limesons in particular. The cosine ones will open to the left or to the right. The sine ones will open up or down. So in this first video, we touched on the basics of graphing polar equations, and we talked about lines in addition to all of these different forms of circles. So we know r equals a is a circle of radius a centered at the origin, and we know how r equals a cosine theta and r equals a sine theta behave. So a can be positive or negative, and a represents double the radius of said circle. So remember, the cosine circles are going to open to the left or to the right. The sine circles are either going to open up or down, depending on the sign, the SIGN sign of a. So with that, we'll see you in the next video.